Okay, so we are approaching the end of the course, and today we'll continue talking about coherent state path integrals. And the first hour I will devote to bosons, which is what we started doing last week, and then the next hour we'll move to fermions, and there you'll see we have a problem, how to generalize it, which I'll explain, but of course there's a way to do it just the same. And okay, so I just remind you what are coherent states. We define coherent states as states denoted by complex set of complex numbers phi, where phi is actually a vector of many components, where alpha are single particle states, some kind of a complete basis of single particle quantum numbers, and the coherent states are defined so that for every alpha, phi is an eigenstate of the annihilation operator A alpha with eigenvalue phi alpha. And phi's, all of these are complex numbers. What we did last week, we arrived at an expression for the partition function for a thermodynamic system of bosons with some Hamiltonian, where let me first write the definition. This is the definition of the partition function, which gives us all the thermodynamics, and here we are working towards the end of semester. These are our units, h bar and k Boltzmann are 1, so that beta, the parameter beta, is just an inverse of temperature. And h here is a Hamiltonian that, let me write it here. We would like to think of the most general form of, let me write here, H grand canonical, where H grand canonical is H minus mu n. I will define it in a minute. So actually, let me write it here already. Okay, and H contains one body term, which is generically can be written in this form, but of course we can always choose a basis where it is diagonal, and then there is an interaction term. Where the parameters of the interactions are, there are some 4 indices generally, A alpha dagger, alpha prime, gamma prime, gamma, and you can also have higher order terms, but usually we're not accounting for them explicitly. What we showed last week was that you can present this as a path integral, and I'm just writing the result that we arrived at. It's an integral over many variables. I'll remind you in a minute what is the definition. E to the minus s, well, and now let me define, so first of all I want to define this differential. So this is what we get if we divide our imaginary time axis with length beta into capital N time steps, and then we have many variables fields, where for each time slice and for each alpha we have a field psi of alpha and tau. So here the fields here are psi of tau, which is this psi of tau is the continuum limit of index alpha, continuum limit of psi j alpha, where j defines the time step. Okay? Just reminding, this is from 0 to beta, where j denotes the time step index, and the difference, d tau, goes to 0 when n goes to infinity. So the differential is a product over all j going from 0 to n minus 1 of and the product of all alphas of d psi j alpha bar, d psi j alpha divided by pi. Okay, that's a definition. And now what is S? So today I want to divide S to two parts. One is a one body part, which is a completely quadratic expression in terms of the fields psi and psi bar, that includes from the Hamiltonian only the non-interacting part, only the single body, and then there is an interaction term that is more complicated, and we'll see later how to deal with it, but let's first just separate them, okay? Where now I'm writing it explicitly, so S naught is an integral d tau from 0 to beta of, let me write it like this, d tau plus, sorry, I want to so I'm missing here one more term, sum over alpha and alpha prime. I just want to write everything as one expression. So here we have psi bar alpha of tau times d tau minus mu delta of alpha prime plus epsilon alpha prime this is the S naught. Okay, so what it includes, there is, first of all, there is a term that includes a time derivative. Okay, psi bar d tau psi, and that's diagonal in alpha. So for each alpha we have it. Also, the term that comes from the chemical potential is multiplying the number operator, and in the path integral, this term appears just as a term, sum over alpha, psi bar alpha, psi alpha, so it's the same alpha. That's why we have here the delta. And epsilon, in principle, can be non-diagonal. Okay? Okay, so that's the most generic way of writing it. And you can easily see that if we find a basis where epsilon is diagonal, then it will just be one sum over alpha integral over tau. Okay, so it will completely decouple between different quantum numbers alpha, but still we have a time derivative which makes it non-local in the imaginary time. Okay, and that we can immediately correct when we do a Fourier transform. So we'll get to it. Let me just, for good measure, write what is S8. The interaction part is just the field expression for the interaction term. So I just copy the same thing, but I replace every operator A dagger by psi or psi bar. Okay, that's a very simple prescription. The V's are parameters, just numbers. Okay, so this is what we get. Psi bar. And sorry, I forgot. Sorry. The integral, sorry. So it's, the action is an integral d tau, 0 to beta, a sum over, let me take the 1/2 outside of the, so I'm sorry for mess. 1/2 integral from 0 to beta d tau, the sum over alpha prime, gamma prime of the V, gamma prime, and then we have a psi bar alpha, psi bar alpha prime, psi gamma prime, psi gamma. Okay? And in all these expressions, all these psi's are at the same tau. Okay, all of them are at the same tau. Okay, so the interaction part is local in time or in imaginary time, but it can have different indices for the quantum numbers. Okay, so this is the most generic part, and one point that I forgot to mention here, and it's very important, is that the definition of psi tau is that it has periodic boundary conditions. Okay, because the way we got this path integral, which eventually should give us a trace. It's a sum over states between one state and the same final state. It forces psi of 0 to be equal to psi of beta. So it's periodic boundary condition. And therefore, if we think of it as a function of tau, it's a function that lives on a circle. It's basically a periodic function with period beta. Okay? Now, therefore, if we want to get rid of the derivative here, and get something that is just a sum of numbers. And we go to Fourier space, and we define psi alpha of tau for each alpha is 1 over square root beta, there's a normalization of the factor, times, this is a Fourier expansion, and it's a Fourier series. It's a discrete sum over index n. N is going to be an integer. The coefficient psi n alpha, the Fourier coefficient, e to the minus I omega n tau. Okay? Well, what is omega n? These are harmonics of a basic frequency. Okay, so it's a periodic function with period beta. The basic frequency is 2 pi over beta. And therefore, we have a sequence of frequencies, which are called Matsubara frequencies. And this is their definition. It's 2 pi over beta times n, where n is an integer. Or we can also write it, taking into account that beta is nothing but the inverse of temperature. It's 2 pi times temperature times n. Okay? All right. Good. So let's put this definition in the box. And now let's see how the definition of the Matsubara frequency, or this expansion, simplifies our expression for S naught. Later, or very, very soon, we'll see that it doesn't help much with S interaction, but the S naught can be simplified. But first of all, let us choose a basis, alpha, where epsilon is diagonal. Okay, and then here at least we'll have only one sum over alpha. Okay, so I'm now rewriting this S naught. This is when for epsilon alpha prime, which assumes the diagonal basis, whatever it is for a particular problem. Then S naught is, let me first write it in the time domain. So there's just a sum over alpha. So d tau plus epsilon alpha minus mu psi alpha tau. And let's first look, so you see it's already diagonal in alpha, but it's non-local. Sorry, this is of course derivative with respect to tau, not really time. Okay, so one can easily see, I'm not doing the algebra, but it's trivial. Actually, let's just do the algebra for one term. For shortcut notation, let me call this quantity, which is the epsilon alpha minus mu, psi of alpha. Okay? It's just the energies compared to the chemical potential. So inside the sum over alpha, we have one term that is just sum over alpha psi alpha bar psi alpha times psi alpha. Okay? But now what I'm going to do is to express psi tau and psi bar of tau as Matsubara sum. Notice that for psi bar, now I'll have psi bar of n alpha, and the exponent will change sign. Okay? So you're going to get sum over alpha, psi alpha, and now I have a double sum over n and n prime of, and I have a factor of 1 over beta, okay, just an overall factor. And inside the sum over n and n prime, I have psi bar of n alpha, psi n prime of the same alpha, times e to the what is it? So it's I omega n alpha minus omega, sorry, it's omega, there's no index alpha here, omega n minus omega n prime times tau. Okay, this is just the double Fourier sum, but now I have to integrate. The only tau dependence here is in the exponent, okay? And we are using the fact that integral from 0 to beta d tau of e to the I omega n minus omega n prime. What is it? So if n is not equal to n prime, we're going to get 0 because it's with periodic boundary conditions, right? But so the only case where we don't get 0 is when n equals n prime, right? So this gives me a factor of beta times the delta n prime. Okay? And therefore, when I plug it into the expression for the action, I'm going to, after performing the integration over time, I just get a sum over n of psi n bar and psi n, okay, with the same n. So let me rewrite it. But before I do it, let us see what happens with the term that has the time derivative. The derivative in Fourier space is replaced by just I, or actually minus I omega, because it acts on psi. Okay? So you can easily convince yourself that if I let me erase this part, I don't need it anymore. Okay, so if I'm rewriting S naught will now become simply a double sum over n and alpha of psi n alpha bar minus I omega n plus psi of alpha psi n alpha. Okay? So it's completely diagonal in both n and alpha. Okay? In other words, it is and we can split it to an independent sum over all the n and alpha components. So we have here a set of fields. Our field psi is now represented by a very big vector that has all psi. It has two indices, n and alpha. N is the corresponding integer, corresponds to the Matsubara sum, so Matsubara frequency. Alpha is the quantum number, and S naught is separable to a sum over such term, and for each of them we simply have a psi bar psi multiplying by a constant. Okay, so we can actually rewrite it in a simple matrix form. So since psi is a vector, psi bar is the row vector, this expression is nothing but a diagonal matrix. It's a component of a diagonal matrix. Okay, and it's diagonal because we chose a basis where alpha is a good quantum number. Okay, so let's now rewrite our path integral in a compact form. Maybe a second. So we get that okay, so generally we also have the interaction term that I cannot write in a simple way. But let's first, let me rewrite now what do we get for the case that, erase this, for okay, v equals 0. So there are no interaction, okay? If you like, this is an ideal gas in the general sense of bosons. Then we get a partition function that I will denote as S naught, because this is for the free, the v equals 0 case, which is given by the path integral over e to the minus S naught. And here, S naught, I want to write erase all this there. Just write here the definition. So, So S naught, I can compactly write it as psi bar times A times psi, where psi is this vector, psi bar is the row vector of psi bars, okay, and A is a matrix That's what it is. Okay, this is a, I don't know if you're familiar with this notation, but it means that it's a diagonal matrix, where on the diagonal we have minus I omega n plus psi. Okay, and just for a reminder, psi alpha is energy minus mu. That's a definition that we'll keep using. Okay? Okay, so in fact you can, of course, write it in this form also when if A is not diagonal. Okay? You can do that, but then it's not easy to calculate. But you can, if you find a diagonal basis, then you actually know how to solve this integral, right? It's nothing but a Gaussian integral. And there's one thing I forgot. You also want to write the differential that before we wrote as a continuum limit of path. Now, in terms of the discrete Matsubara frequencies, it actually can be written in a much simpler form. So if I write it in terms of the components psi and alpha, not psi alpha of tau, it is nothing but let me write it like this. So it's a product over all n's and all alphas of d psi n alpha bar, d psi n alpha, divided by, there's a factor of pi, but also a factor of beta. Why a factor of beta? Because when we change variables from psi tau to psi of beta, to psi n, sorry, there is this normalization function, the factor. Okay? Okay, so I want to emphasize that this definition, this factor also takes care of the units, so that the result for the partition function will be a pure number, right? It shouldn't have any units, okay? It should be just a number of states. Okay, so this is what it is, and in fact, it's so let us first write what is the general expression for Z naught. Okay, this is erased already. No longer need the Newtonian also. Okay, so if I just rewrite it like this, I just plug in S naught okay, what do I get? I get First of all, there's a factor of 1 over beta. This is coming from this 1 over beta to the power, let me call it curly n, which represents the number of components, the total number of components, which is all the n's and all the alphas. In fact, it's infinite, but we have to keep a factor beta for each degree of freedom, okay, in this multi-dimensional integral. So this is just important to keep the units right, and then we everything else will just give us a Gaussian integral. Because of the factor of pi here, there's no pi, so it's just the determinant of the inverse of the matrix A. Okay, so actually this is true for any matrix. It doesn't have to be diagonal. If it is diagonal, then the determinant is nothing but a product of all the diagonal elements, right? But this is a general, let me maybe write it right here. If we have, I don't know, Z complex vector, which is Z bar, where Z is an array of complex numbers, e to the minus Z bar A Z is equal to the determinant of A to the minus 1. This is a mathematical formula that you're going to prove in your homework, okay? And the way to prove it is just to write it in a diagonal basis, and then it comes out easily.
You mean 1 over that, right? Not the inverse of A.
It's no, it's the determinant of the inverse of A. Yes. It's
1 over
no, it is, yeah, it is the determinant of A to the minus 1. Yes.
Right.
It is correct. Yeah.
Okay.
Okay, but if you think of a diagonal basis, then of course, if these are the elements of A, then A to the minus 1 will be 1 over. Okay? Okay? So this is general. Let me put it in the frame. Yes?
If there isn't a minus in the exponent, so it's a determinant of A. I mean, the 1 over is because the minus in the exponent?
Yes. So it's a determinant. Let me make it clear. It's a determinant of the inverse of the matrix A. Okay? Now, if A happens to be diagonal,
sure,
then A minus 1 is just the diagonal of 1 over the same thing, right? And therefore, in this case, Z naught will just be a product over all n and alpha of 1 over beta times, sorry, this is omega n. It's omega n. Okay. Omega depends on the index n, and psi depends on alpha. Okay, sorry about that. Plus psi alpha. Okay. Now you see how the units cancel, because for each term in the product, we have beta as inverse units of omega and psi. Okay, under our units, right? That's all. That's a very simple expression, and then what will be the free energy? If that is the result, then a free energy, which is minus 1 over beta log of z, will just be minus, so then the beta will cancel and we'll get minus a sum over n alpha of the log of this thing, and because because it's 1 over, there's a plus. Okay, that will be the free energy.
Why is the beta cancelled?
First, it should, right? It should have, there's a 1 over beta, okay? And here you have just a factor beta for each.
Yes, but
sorry. No.
It's inside the line.
No, sorry, you are right.
Units of
No,
energy.
I was sloppy here. Yeah, you know, so that, yeah. So let's just write it. Sorry, you're right. This is there's a beta. And 1 over beta. So it doesn't cancel. Cancellation is for something else. So it's minus 1 over beta. Plus. Yeah, it's a plus because it's this is in the denominator. Okay? All right, this is what it is. Now you can bring it to a form that is more familiar to you from statistical physics. If you remember what is the definition of the omega n's and perform a so-called Matsubara sum. So there are formulas how to do it. You'll discuss it in the tutorial next week. That's a technical point. But you can bring it to a form that is familiar for you for the ideal gas of bosons. Okay? This is about the free energy. Now what about another thing that you can calculate exactly for the case of free bosons? Again, this is without the interactions. Let me now define what I want to erase. Yeah. Let me define here a Green's function. So what is a Green function? I want to look at, let me define Gn alpha n prime alpha prime is the expectation value of psi bar psi. Let me define it in this order. Okay, that's a definition of a matrix element of a matrix that I call G. This is a matrix element relating n alpha to n prime alpha prime. And what do I mean by expectation value? Okay, it is just a usual definition. It's 1 over the partition function times a trace over e to the minus h times the quantity. Okay, that's a general definition of an average of an operator, but in our case, since we are using a path integral formulation, you just put the psi inside the integral. And here we have, okay, that's a definition, that's a general definition. Here S is not necessarily S naught, okay? Okay. So, and S is a functional of many variables, and here you're just calculating the average of one pair. Now, if we now assume that there are no interactions, just S naught, and we choose a diagonal basis, then we can actually calculate it. So let's do it. So, and I define it as G0. Again, for non-interacting, this will be our convention. What is it? It's the same thing with S naught. So it's 1 over Z integral psi n alpha e to the minus S naught. But what is S naught? S naught is just psi bar A psi. Okay? So we actually know how to calculate this Gaussian integral, right? What is the result? So I remind you that, again, if you have just a single complex variable, and you look at Z bar Z, e to the minus, what do you get? Oh, actually, let's do it for, yeah, okay. If this is just a single variable, then if you have the correct normalization, without this you get a determinant of a to the minus 1. But after you take this and divide by the integral without the factor, what do you get? Just A inverse, just A inverse. Okay?
Right.
So here this is what you get. So this is nothing but the inverse of A. Sorry, this is the matrix element. So in general, this is the n prime alpha prime element of A minus 1. So let me write it here. Okay, this is what it is in general. But if we choose a diagonal basis, yeah.
Should it be delta?
So I'm saying this is general. This
Yeah,
is
but
in
generally, if it's not delta, it will cancel.
No, if S naught, if A was not diagonal, it will not cancel. But you are right that it will, if you choose a diagonal basis, then of course it will be. Okay, so this is for, by the way, it's always diagonal in n. Okay, it's always diagonal in n. To be diagonal in alpha, you need to choose the correct basis, that's all. So let me just use this assumption. And then this becomes nothing but delta n n prime, delta alpha alpha prime, times what I will call G naught of n alpha, where, take this second ways for now. Where here G naught is one over okay. However, I can actually, so this is for choosing a particular basis, but more generally, since G naught, the matrix G naught is nothing but the inverse of the matrix A. Okay, so if I have a most general action, which is something like that, okay, the most general A, I just prove to you that G naught, the matrix G naught, is the inverse of A, right? So as a result, we can actually rewrite S naught in terms of G naught, okay? It will be G naught minus 1, okay? So let me write the final
So
result. Yeah.
you're considering the differential operator as the inverse of the Green's function, right? That's what you meant? Like you went to Matsubara space and
Yes.
that like this is the representation of the differential operator in omega.
Yes, that's right. Right. So this minus I omega n can be traced back to the differential with respect to tau. It's the time derivative.
Right.
Okay, the time, right.
And this is the equation L times G is delta.
Yes, yes, yes.
But-
Right. Yes.
okay.
So quite generally, if you have non-interacting bosons, I can write the path integral like this with S naught. Actually, let me just write the most general result. Okay, so okay, that's the final result. Okay, we can just express S naught in terms of the inverse Green's function, where we keep in mind that this is its definition, and in a diagonal basis, it takes this form. Okay, and There is some physics you can sort of get from it, because if we look at this expression and forget now about the fact that omega are some Matsubara frequencies, which are discrete set of products of the temperature. But let's just go to zero temperature. Zero temperature, omega n becomes a continuum, right? Because we have a Fourier series, but with very small step. Okay, let me write down again the expression for omega n. It's 2 pi times t and times n. Okay, this is the definition. And in the limit that t goes to 0, it's becoming a continuum. So the sum over n goes to integral over omega. But let's just look at this expression and think of omega as representative of some frequency. So you see that what this describes is a resonance. Every time we hit the particular frequency, such that there is a pole here, okay? And the fact that there is a minus I here is related to the fact that we represent it in imaginary time. If we go to real time, it will really be a resonance. Okay? There is going to be a singularity every time that we have an excitation, a bosonic particle with energy psi alpha. Okay? All right? Okay, so we see that to make a long story short, if we have non-interacting particles, of course everything becomes simple. So this is nothing but doing what you are already familiar with, which is the statistical physics of ideal gases. Okay, and the only thing we have to keep in mind here, we have to find a good basis to describe it, a good basis of quantum numbers alpha, and that's it. And then everything is simple. You only have to solve Gaussian integrals. By the way, one of the things, some of the physical quantities we can calculate, apart from the free energy that I already mentioned, we can, for example, calculate the occupation of bosons at the state alpha. What will be the result? We already know the result, right? It's Bose-Einstein. But in fact, how to get it systematically?
It's Bose-Einstein at 0 temperature, right?
No, it's Bose-Einstein. So let me write it down. I will not do the algebra. You are going to do it again in a tutorial. But let's see how you do the calculation. I no longer need the definition. So what is, let me first ask, what is the occupation? It's the expectation value of the number operator n alpha, which is, let me write it explicitly, it's A dagger alpha, A alpha. But if we express the expectation value in a path integral language, which is, let me now just write a general definition, which is integral that's just a general definition. And since we are using a path integral language, we can replace the A and the A dagger by psi and psi bar. So this is psi bar alpha, and deliver 3 writing it with care, okay? And it's psi bar of alpha psi alpha at the same tau, okay? Because it's local, it's just yeah, the same time step.
So it's
And-
bunching.
Hmm?
It's the bunching. It's not like bunching of photons.
It's, I don't know what you mean. It's just
Like in quantum optics, when you're bunching and anti-bunching.
yeah, if you like, yes, but it's nothing but just the occupation. Okay, it's the
Yeah, but from here they're
yeah,
coming
of course,
at the same
of course,
line.
it does give you. Okay, so yeah, of course it gives you something that represents a bunching of photons, if you like to, if you think of it as photons. But generally, for any bosons, this is actually also for any fermions. But for bosons, we know how to calculate this already. But this is what we need, but we saw that the simple representation of the action and of the Green's function is not in terms of time, but in the frequency domain, right? So we want to replace these psi's by their Matsubara representation. And one can easily see that because it's the same tau here, what you're going to get is a sum over n of, in fact, okay, if I want to be careful, there's a sum over n and n prime, but then because it's the same tau, you're only going to get a result from n equal n prime. So I already write it like this. And now you have, let me just show that. Yeah, so there's a 1 over beta psi n psi n. Okay, right? So here I use the fact that it's diagonal in the Matsubara frequency. And what is this? It's nothing but what I call the G naught. Okay. So let's rewrite it. So n alpha, the occupation is 1 over beta. Actually, there is yeah, it's 1 over beta, sum over n of G naught and alpha, or to be explicit, you can write it as a sum over n of T. Now I'm using temperature, which is 1 over beta in the numerator, and in the denominator I have minus I omega n plus psi of alpha, where omega n are given by integer products of 2 pi t. Okay, so this is 2 pi t, and then you have to sum over all integers from minus infinity to infinity. So this kind of mathematical expression is called the Matsubara sum. And there is a prescription how to do it in general. You will discuss it in the tutorial. Sarah will present it next week. But what is the result? You already know, I think. This is exactly what it gives. Which is the Bose-Einstein statistics. Okay? Okay, and So this exponent in the denominator encodes the fact that in the sum it appears. Actually, this comes from complex analysis kind of thing. Okay, if you look for what are the poles of these functions, you see that they are exactly these Matsubara frequencies. Okay. Okay. So we basically recovered things that you already know, but this is because we assume that interactions are zero. And this is not useful, you know, this is just a fancy way of getting what you already know, okay? But the nice thing about the path integral is now if you have interactions, there are various ways in which you can take care of them systematically, okay? For example, the simplest thing you can do is do perturbation theory, assuming that interaction is small. And the reason that the calculation, and you can do it to any order, the nice thing about representing everything as a path integral is that you have to only solve integrals. Okay? It boils down to calculation of integrals. And perturbatively, there is, you can calculate expectation values of various quantities, various products of operators to any order. And in fact, if you're making perturbation theory on a non-interacting system, you have a Weeks theorem coming in again, but now it can be represented in a path integral language. Let me first point out why interactions are complicated and why it doesn't help to go to Matsubara space here, okay? So, okay, so erase this. So let's now rewrite. I have an interaction term, which is this expression, and first of all I want to represent it in terms of the variables psi and alpha, the Matsubara basis. How do I do it? Here I have a product of 4 fields, okay? Each of them I can write as a Matsubara sum. So how many sums I will have just when I plug it in?
4.
4. Okay? And the problem is that I have only one integral over tau. Okay? So in other words, I'm going to get something like that. Let me first write the sum of their indices, alpha, alpha prime, gamma, gamma prime, or V, alpha, alpha prime, gamma, gamma prime. And now I do, this is where I would like to do the integral d tau from 0 to beta of, and now what I do is I expand all of these fields as Matsubara sum. I have a normalization factor that is how much? 1 over beta square, right?
Right.
So let me, for good measure, let me keep it here, 1 over beta square. Okay, and now I have the sum over n1, n2, n3, n4, of psi bar n1 alpha, psi bar n2 alpha prime, psi n3 gamma, gamma prime, psi n4 gamma, and I have in the exponent e to the I omega n1 plus omega n2 minus omega n3 minus omega n4, all that multiplied by tau. Okay?
I forgot the integral.
I forgot the integral. Thank you. Sorry, I wrote it on. D tau 0 to beta. Yes. Okay. Right. Okay. Great. Now I want to get rid of the time dependence. So, and it's again a very simple calculation, because the only thing that depends on tau is this exponent. And just like what we saw before, it will give us a delta where you get just a factor of beta only for the case that n1 plus n2 equals n3 plus n4. So I have only one delta, one constraint on my n1, n2, and 3. In other words, I reduce my indices from 4 to 3. So I'm still left with 3 different indices. Okay, so the Matsubara representation became more complicated than the time dependent, because the time representation is at least local. Okay, so I don't gain anything by doing this. However, if I want to do so, let me just write what is the result of this will be that I will replace, let me just write after I take all of this, I perform the integral, it gives me the one factor of beta will cancel, and what it will give is just this part. It will give me 1 over beta, then there is a sum over n1, n2, n3, and then I get psi n1 alpha, psi n2 alpha prime bar, psi n3 gamma prime, and psi of minus n1 minus n2 minus n3 of gamma. Okay? That's the result, and that I have to multiply by V and do the summation. So a lot of indices here. But what if I want to treat it perturbatively, and that's only like the simplest thing to do in order to make progress. I will have to compute expectation values of such products of size. Okay, and if I want to go to second order, there are going to be 8 of them. But fortunately, if I do it in as a perturbation over a non-interacting action S0, which is Gaussian, every such term or every order in the expansion can be computed using Wick's theorem. Okay?
Can you say
So-
it again? Can you repeat the last few sentences, please?
Yeah. So what I'm saying is, if I want to compute, let's say z, okay, from which if I take the log, I get the free energy, then I have to I can compute it in this way. I can write e to the minus s naught and e to the minus s interaction I can now expand. Okay, I can expand it into a power series, and I can do it to any order. And of course, if I take the log of this, I have to be careful with keeping track of the orders. But what I want to point out is that every term in this sum will just give me an expectation value of a product of operators calculated in a non-interacting action, which is Gaussian. Okay? And therefore, there is a formula how to compute it, and this is the generalization of the Weeks theorem. Yeah, so it's so if I have a product of N1, alpha 1, N2, alpha 2, blah, 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 blah. There can be many such things, and psi of N1 prime, alpha 1 prime, psi of N2 prime, alpha 2 prime, dot. Okay, there can be many fields here, but I want to have the same number of psi bar and psi, otherwise it vanishes. Okay, this thing is just, and again, this is for bosons, remember? It's all the permutations of the contractions. So basically, it's exactly the same weak theorem we had all along. We want to pair this with this, and then do this with this, etc. But we can have all the possible pairs, and we sum over all the pairings of two particle or two field contractions, and these are nothing but the Green's functions, right? So it's just a permutation over all the possible contractions. N1, let me write it like this, N1, permutation of N1 prime alpha 1 prime times the same thing with N2, and the permutation of N2 alpha 2 prime, and then there's just the product of all the possible pairs. Okay, that's what it is. So, for example, if you only have only psi bar, psi bar, psi, psi, what you get there, for each choice of contractions, you have just a product of two Green's functions. That's all, right?
Right.
Yeah, and then you have Hartree and Fock and all of that. So, for example, if we look at the free energy, maybe we'll do it next week. I don't want to spend time on it now, but if you do the free energy, take the log of this and do a systematic expansion in powers. The leading term, which is just first order in the interaction, will give you the usual Hartree fork, but now it's generalized to finite temperature. Okay, that's the extra few cents that we got from doing a path integral at finite temperature. Okay? So not only for the ground state, you can also compute it for arbitrary temperature. Okay? Okay, so this is, I think, all I want to say for now about bosons. Any questions? Okay, so the last 10 minutes before the break, I want to start talking about fermions, and we want to do so we already see that there is here something very useful about this representation is that we forget about operators, commutators, all that. We just, any complicated many-body problem can be reverted to some kind of calculation of integrals, essentially. We already saw, remember that when we did the Hartree fork, for example, one of the problems we had is that it looked like a kind of a black magic. We made an assumption that we can replace some operators by the expectation value, okay? And we could also do more. We could do a mean field theory that is more sophisticated, assuming that the ground state is non-trivial, right? This is what we did for the BCS. But there was a bit of hand-wavy flavor to it, in a sense, because we made an approximation without specifying exactly what are the corrections. Okay? Here we can do it systematically. Okay? So we have an exact expression. The exact expression is this, right? There is the whole action is in the exponent. We know how to write it. Okay, it's a function. It's a very non-linear, non-quadratic function of many variables. Fine, but if we want to do an approximation, we know what we are doing, and we can always compute the corrections. Okay, and see what we're missing. So we can go beyond, and at least to second order in many cases, you can go beyond the mean field. For example, in the problem of superconductivity, you not only get that there is a gap delta and the gap equation. That's the Hartree fork, not Hartree fork, the mean field level. You can assume now, okay, maybe delta is fluctuating in space. Okay, then fine, or finite temperature. How does it change with temperature? How do we see that there is a critical temperature? We can compute the fluctuations, okay? And they're actually not very complicated, and you can get a so-called Landau-Ginzburg theory, okay? So we can do more than we can do in the, like just mean field. Okay, so what's the problem? We would like to be able to do it for electronic systems, for example. I just mentioned superconductivity. The microscopic model was interacting fermions. And so we would like to have coherent states for fermions, but we have a problem that has to do with a very weird property of fermions, and that's the fact that their basic operators, the A dagger, are anti-commuting and not commuting. So let me show you why there is a problem. And I remind you that this is the definition. This is the definition of coherent state. But now, if you want to discuss fermions, change color. Then A alpha prime dagger. These are now anti-commutators, okay? Let me remind what it means. So, for example, if I, and of course, so this is one. What? Sorry?
It was my phone, sorry.
Okay. So maybe, okay, so, yeah, this is 0, right? For both A and it's 0. So, this actually means that if I change the order of alpha and alpha prime, I get a minus sign. Okay? Okay? Now, where is it? So, yeah. So now I want to, let's assume that I have a fermionic coherent state. Okay, I still don't know what it is, or whether such a state can be realized or expressed mathematically. But let's assume that just like what we had for bosons, we have a state that for any alpha, it's an eigenstate of the annihilation operator with an eigenvalue. I call it eta, just to differentiate it from bosons for now, okay? Okay, and what is eta? Just like we had for the bosons, it's some array of numbers, of complex numbers, so that eta bar is the row vector of eta alpha bar. Fine, okay. But now this eta contains many alphas, and I can always look at A alpha prime acting on the same coherent state, okay? So in the case of the bosons, what this would give me for bosons it would give me, I first apply A alpha prime, I get eta alpha prime times eta alpha, just the product of two numbers. Okay? But now if I do it like this, so let me first apply A alpha prime. This will give me eta alpha prime, but then I apply A alpha and I get eta alpha times the state. Okay? Well, now eta alpha prime are numbers. But on the other hand, I have this equation. So if I change the order, I get, so this is equal, we know that it has to be equal to minus A alpha prime, A alpha acting on eta. But this we can also explicitly write, and it will give us eta alpha prime. I'm keeping track of the order, notice that. And I'm getting here a very strange equality that we can accept that it's correct for operators, but not for numbers, right? Numbers are C numbers. They're numbers that they're commuting objects. And here we find that this has to equal. Okay, so one possibility is that it's 0, and that means too bad. There's no way we can do path integrals for fermions. I don't want to say impolite words. Not good. But there's another possibility, and I confess I don't know what was the motivation, but already in the 19th century, some German mathematician named Grassmann proposed an extension of the family of numbers to a set of variables that he called the Grassmann numbers or Grassmann variables. And these are, so if you like, this is an extension of the numbers that we know, just like we go from real numbers to complex. We can do other things, and one of the things we can do is, of course, such a relation cannot hold for regular complex numbers. So the etas cannot be, if they are coherent states, these are not complex numbers, but they can be Grassmann variables, and Grassmann proposed so that's what he proposed, a definition of an algebra of numbers that their products, pairwise product, depends on the order in such a way that if you exchange two, you pick a minus sign, or more generally, if you have a product of many Grassmann variables and you do a permutation, if it's an odd permutation, you pick a minus sign. Okay? So they are numbers, they are not operators. They're not operators. They are numbers in the sense of but they are an anti-commuting. And of course, then if we want to do algebra, if we want to do to define derivatives and integrals and everything we do with regular numbers, we have to revisit, okay? Because, so one of the consequences of this is that if I take just one Grassmann variable, what is the square of it?
0.
Exactly. Right? So, or in other words, eta to the n is 0 for any n larger than 1. Okay? So, this actually is very interesting because if we think of functions of these variables, in their Taylor expansion, we cannot have more than linear order in each of the Grassmann variables. Okay? And stuff. So you have to revisit all the mathematics rules, and if you do it systematically, and there's a way to do it systematically, then you can work with them. Okay, and they will allow you to do path integral for fermions. Okay, so that's a good place to make a break, and let's meet it. Let's continue. So yeah, so let me write here a set of rules for how we do mathematics with this Grassmann variables. Close the door. Okay, so first of all, the first rule is that if we have a set of variables, we write it like this. So it's a set of etas with some indices, and they have to obey anti-commutativity. And second, which actually follows from this, is that eta to the n equals 0 for any n larger than 1. Now, if we want to write down so we want to be able to look not only at these variables but any function of them, right? Because eventually all our physical quantities will be represented by some power series or whatever, some function of these variables. So how we define a function of, let's assume that it's generally going to be a function of many variables, right? In general. The way to do it systematically, and by the way, this is also what we do for functions of operators, we use a Taylor expansion, okay? That's should always work for any reasonable. And of course, I want to assume that f of the variables is some well-behaved function. It's not some crazy thing. It's an analytic function if it were for regular variables. Okay, so how will the Taylor expansion look? It will be quite generally first of all, we can write it as a sum, just like any Taylor expansion. It's the sum of all powers of the derivative of f. So it's the nth derivative of f with respect to so let me, sorry, I also want to have here yeah, let me write it generally like this. So it's 1 over n factorial, and now we have a summation over all the indices I, or all the sets of indices, and here we have the nth derivative of sorry, d eta 2 d eta n, and the derivative is calculated for all the etas equal 0, okay, times the power eta 2 up to eta n. Now notice that each of the variables, each of the independent variables appears only once. Okay, so we cannot have an nth derivative with higher powers of.
It's also
Okay,
because
so you have infinite order, infinite power, assuming that the number of indices here is infinite. You can have infinite order derivative, but each eta appears only once. Okay, this is for a general function of many variables. A special case is, what if we have just a function of one variable? So that actually is very simple, because what can we have? Just the zeroth order is just f of 0 plus the first derivative at 0 times eta. Okay? If we have a function of two variables, we can also have the second derivative is going to be eta prime and so on. Okay? Now, this f of 0, these are just, you look at f is some regular function of a variable, okay? Let's take an example, okay? So, e to the function e to the eta. Oh, sorry, let me write it like this. F of x is e to the x, just the exponential function. What is f of eta? It's first of all f of 0, which is 1, plus the first derivative is again 1. So that's okay. Just the leading or Taylor expansion. Okay. Great. So actually doing algebra with Grassmann variables is very simple in that sense. Right? You don't need to worry about, so all the nonlinear functions reduce to linear functions, basically. That's great. But the other thing we want to be able to do is, I also want to look at derivatives. So when I have a product of many Grassmann variables, I can look at partial derivatives with respect only to one of them. Now that also needs to take care of these anti-commutators. So the fourth rule that I want to include here is that if you take a derivative with respect to eta I acting on eta j is going to be delta of ij. Okay, because if it's I is different from j, you get 0. Otherwise, you get 1. Okay. Now, if I have, let's say I have eta, I take a derivative with respect to eta I, and I act on it on a product of eta I, eta j. Okay, what do I get?
Eta j.
So first of all, so if they were just regular numbers, it's just eta j. But let me show you that actually now we have to be a little careful, right? Because this is also I can also rewrite this product as minus eta j eta I, right? And now I want to treat this as a derivative of a product. If I act on this, I get 0. But then in order to act on eta I need to transfer it to here, right? So in order to get in order to get a consistent result, I have to notice that also the derivative operator, okay, the derivative is also anti-commuting. Okay, so in other words, derivative with respect to eta I acting on eta j. If I want to switch them, I have another minus sign. Okay, so this is the same as eta j, the derivative I, which is so in order to have in both cases the same result, namely that it's just eta j. Of course, here I assume that I is different from j, otherwise it's 0. Okay, so I don't even have to say. But in order for this to be consistent, I must assume that for j different from I, this is minus eta j derivative with respect to eta I. Okay, so not only the Grassmann numbers are commuting between themselves, but also with respect to derivative. Now we can also have expressions like, for example, in the functions, we can have combinations of Grassmann and regular complex numbers. Right? So, but regular complex numbers are commutative. Okay, so another rule, if you like, is you have Ci eta j. So Ci, Cj, this is commutative. Okay, I can. Well, C is just a regular complex number, and of course the product Ci times eta is itself a Grassmann variable. Okay, so any combination, any linear combination of Grassmann variables is acting like a. Okay. Okay. What else do we need to do calculations? And in particular, notice that we want to get to integrals because the whole idea here is to get path integrals in terms of these funny objects. The other thing, there is another rule that I want to mention here. Let's call it number 6, but it's also important. So if I have a set of operators, A and A daggers, but let's just look at A, or any operator, actually, yeah, let's talk about annihilation operators. So I have a set of operators, these are operators, and I also have a set of Grassmann variables. So A and eta are also anti-commutative. Okay? Okay, so operators anti-commute, Grassmann, and also operator Grassmann are anti-commutative. Okay? Okay, so this takes care of any combination that has products of things. We know what to do. If we want to exchange the order, we just have to maintain a minus sign times the parity of the permutation that we do. And the last and very important thing I want to mention is integrals. Okay? So, with your permission, I erase this. You remember it.
And we can define complex conjugate or something like here?
No, so we can't. We can't. Okay? Right? Because a complex conjugate, okay, so that's very important. What is a complex conjugate of a regular complex number? It's something that if we multiply by the psi times psi bar gives you a positive definite object, which is the absolute value squared, right? But for Grassmann variables, we cannot have such a thing because, you know, if we could say that eta, there is an eta bar which we can write as eta square, then what will be its square? It's the square of this should be just eta to the 4, right? Just the square of a positive. But this is 0. Okay? So there's no such thing. And that's very important because we will have an eta bar and we have to admit that it's not a complex conjugate. It's just another independent Grassmann variable. Okay? Good. So now about integrals. I'm not proving and explaining. It's kind of, I mean, there is a way to justify it, but let's accept it as an axiom that works, okay, and it makes everything consistent. The integral over eta, okay, I'm not writing the boundaries because it doesn't really have meaning in the usual sense. It's like integrating over all possible values of eta. What is this going to be? It will be 0. Okay? And one way to think about it is that you know, for any eta there's a minus eta, you know, because it depends on where it sits in a product and so on. So the integral has to be 0. Okay, so this is one result. Now, however, the eta of the integral over eta, this is non-zero, and in fact, it's going to be 1. Okay?
This is like the measure. I mean, what is
I'm not
the
sure.
integral of
Yeah,
d
I'm not sure what. I mean, it's just if you go to the roots of the definition of what is an integral, you can define it in this way. This is easier to understand. It's just what I said. It's some symmetry argument. So this is going to give you symmetry over anti-symmetric objects will give you 0. And this one has to give you something non-zero, symmetric, and the only symmetric combination is. So it's like the numbers associated with this can go between 0 and 1. Okay?
So the integral
So-
and the derivative do the same thing?
Ah, okay, very good. Now, first of all, here I'm done telling you how to calculate integrals. Why? Because every function of a single variable is just its linear Taylor extension. It's extremely useful, right? And if I have many variables, then I have double integrals. Then every variable can be expanded to its linear order. Okay, we'll see a concrete example, very important one. But having this, accepting this, now let's calculate an integral of any function.
Can I ask a question?
Yes?
What happens if f diverges in 0? Let's say I want to write the square root of theta. How can I do it?
Excellent question. But so the question that's a problem because it's not analytic at 0. Okay,
Yes.
right? So the answer is I don't know. I know about analytic functions. I think there is a problem with the square root because also by the way, for complex numbers, it's a delicate object, right? It has a branch cut, right? So, in a sense, even for regular complex numbers that you're more used to, it's not a single valued function. So here we have a different problem with it. So actually when I say, so when I mentioned that any function can be written as a Taylor series near 0, if it's near 0, then it must be analytic at 0. Otherwise, I don't know.
So basically there is no good interpretation for
There's no good, I mean, maybe you can cook one because it's something that when you square it, you get eta. I'm sure it has been considered, but for physics program, it doesn't appear. Okay. The reason it doesn't appear, I mean, we actually in practice, for our purposes, I mean, maybe you can use it in mathematics for other things. In physics, usually appears as just products of values. That's the kind of functions we get. Okay, or any analytic functions. Everything is analytic. So for any analytic function, the integral, it's exactly as you say, something very funny happens here. So the integral of an arbitrary analytic function is, let's do the Taylor expansion. Taylor expansion is this. The first term will give you 0. So I'm left with the second expression. So it's f prime. And then it's multiplied by the integral over eta, which is 1. Okay? Now, but this is what is f prime. It's nothing but the derivative of with respect to eta of f of eta, right? Because f of eta is just f prime plus f prime times eta. If I take the first derivative, I'm left with f prime of 0. So an integral is a derivative.
At 0, actually. Right.
No, an integral over the variable eta is like a derivative of the same function with respect to eta. Okay? Okay, so maybe, one way of understanding it is that these Grassmann variables are really kind of binary objects. They're defined modulo square, right? So they can be 1 and 0s in a sense, and if you're integrating, you're adding. If you're taking a derivative, you do the opposite, but you're back to the same. So this operation is it's a Z2 thing, right? There are only two options. Okay? Okay, now this is extremely useful, right? Now let's use it for something that we really need for doing coherent state path integral. And for eventually I want to have an explicit expression for these coherent states. This is for just like what we had for bosons. That's the goal eventually. So let's take an example of a two-variable function, to which we want to calculate an integral, and that will be a Gaussian. Okay, so. So suppose I have here now two independent variables which I call eta and eta bar. Okay? And I want to compute the integral okay. Now A is some number. If you want, it doesn't actually have to be a real positive number. I mean, it appears like it should be, but it doesn't have to be. Okay, just a number, regular number. And the eta and the eta bar are independent Grassmann variables. How do we compute this? What is the result of this integration? So I do a Taylor expansion of the function. And once again, I only have very few contributions. The 0th order will give me 1, right? The next order will be, if we take the first derivative, we'll get at 0, the first derivative will give me 0, right? So the next non-trivial contribution is linear ordering the whole thing, right? So it's 1 minus eta bar A eta. Okay?
Would be like half.
No, why half? No, just linear. It's a linear expansion of this function. Okay. All right. And the second order is 0. That's it. Okay. Now we can compute it. Let's because they are independent variables. Let's first of all calculate the first term. What does
0.
0, right? The first term gives 0. Then the next term will give you, now we have to do, so let me just, okay, so here actually I was not careful, okay, I was not careful, because I want to do this. And of course, it's not the same. There's a minus sign difference. Okay, very important. I want first to integrate over eta and then over eta bar. Okay, so then I have to, so the first order will be 0. Now in the next order, I first want to integrate over eta, but and integrating over eta is like a derivative with respect to eta, but in front of it I have an eta bar. I have to exchange it. The A is commutative with everything, so I can put it anywhere. So if I do the exchange between d eta and eta bar, I get plus, okay, A times, let me write it like this, eta bar, eta, okay. I integrate over the eta, I get 1. Integrate over eta bar, I get 1. So this is the result. Okay. So let me write down. This is a very useful formula. Okay, this is the result of a Gaussian integral for Grassmann variables. Okay, how is it different from usual complex Gaussian integral? Remember, what did we get for a complex? So for complex, this is pi over a. Right? First of all, there's a factor of pi, but more importantly, the factor of pi is just, we could vary it in the measures, but here it's 1 over a, here it's a. Okay? Now, if we can easily extend it to a multivariable integral, right? Because we can have, just like what we had in path integrals, we can have a series of eta alphas. And then we can, if we look at, let me define here. Sorry. And now my eta now is not a single variable, but it's an array of many eta alphas. And this measure is defined to be a product over all alphas of d eta bar alpha, d eta alpha. So for each alpha, I actually have 2 independent variables. I call them eta and eta bar, but they're really independent Grassmann variables. And this is just a definition of this differential. So this integral is what it's giving. So the terminal, sorry, it's a number, the terminal. Okay, so let me just write it. Rest, okay. That's the generalized Gaussian formula. How do we prove it? A is just a matrix of regular numbers. We can always choose a basis alpha where it's diagonal, and then it's trivial, just a product, a simple product of the alphas. So again, this is a different formula, okay? Different formula for bosons and fermions, okay? And if you like, we can, I'm saying bosons and fermions, I mean complex numbers versus Grassmann, but eventually this is what will come into the path integral, something like that. And in a way, you know, you can, if there is let us define a variable psi that is either complex or Grassmann, depending on a parameter that we call zeta. Remember, the zeta is +1 for bosons, -1 for fermions. So you could generalize this formula to define it as e to the minus psi bar a. Psi is the determinant of a to the minus zeta, where zeta plus for bosons minus for fermions. Okay? Or, yeah, when you say bosons, I mean complex fields versus Grassmann fields. Okay? Okay, great. So because of this formula, so it's different than the one we are used to, but exactly like in the case of the bosons, if we manage to write down a consistent path integral for fermions, which appears as integral over an action, minus an action, and this action is quadratic. We have a closed formula, we can compute any Green's function and any expectation value of a product of fields using the Wick's theorem and everything, except that again we have the minus to the power number of the parity of permutations. So having all this mathematics to our utility, let us now do the path integral for fermions. And we have to watch out that any, so before doing the path integral, I need to find an explicit formula for the coherent state. Okay, so I just assume that you have such states, but I want to be able to write it, to express it in terms of annihilation and creation operator, just like we did for the bosons. Okay, so let me write down the result. Proving that it works is just simple algebra, of course, following the rules of anti-commutators between any operator and any Grassmann and any derivative and any, just keeping track of that. will work out. I think you will have a homework doing it. So I'm just writing the result. So so first of all, let me write how they look. Coherent state. For fermions. Okay, so this is how it looks like. It's very similar to what we had for the bosons, except for a minus sign. It's an e to the minus sum over alpha, and again, this eta is a set of Grassmann variables, eta alpha, A alpha Beger, all that acting on the vacuum. Okay? Right. Now you can I'm not doing now the calculation, but you can easily understand how it works, because if I now apply A alpha on such a state, okay, so we already know how to do calculations. The first thing is to write this nonlinear function as a Taylor expansion. And once again, it's just 1 minus this, right? And now so it's only, we have to keep only its linear order for each variable. And then you can easily convince yourself that when you act on this with A alpha, you get the same state times eta of alpha. Okay? And why the minus? Why do we need the minus sign? Because so when I expand this, I will need to pass A alpha to exchange it with the eta, and that will be anti-commutative. Okay? So okay, so actually, if I'm using my famous zeta, which 1 for bosons, minus 1 for fermions, I can write already a general formula, which is e to the coherent state is e to the zeta okay, this is where zeta appears. It's plus 1 for bosons and minus 1 for fermions. For the Gaussian integral, we have that d psi bar. The differential is also defined a little differently with factor of pi. But let's so in the case of the bosons, there's a 1 over pi, and for fermions there's no pi. But the formula in any case is this is determinant of A to the minus of zeta. Okay? And you'll see a lot of formulas can be written compactly as the same expression, but with a factor of zeta. Okay? Okay, so that's the coherent state. Now let's do Hermitian conjugate. So this is now a quantum state. Okay? And this is its Hermitian conjugate. So what is it going to be? It's 0 times, sorry, so I forgot one on stage to do. So I forgot something. Let's do it here. Okay, so I want to write the Hermitian conjugate of this equation. This is what it is. Right? A alpha dagger equals eta, and now there is something I call eta alpha bar. But it is not a complex conjugate. It is not. It's just an independent Grassmann variable.
What is the relation between the hat and without, I mean, with the guy and without it?
Again,
We didn't define it.
this is the definition.
But what is the connection with the, okay.
No, there is no connection. So again, so we just have to know how to calculate things. I'm giving you a set of rules. They have to be consistent. That's, if you like, the definition of eta bar. However, it cannot be just because of what I said before. It cannot be a complex conjugate. It's not a complex number. But what it actually means is, in practice, if I have now a matrix element between one coherent state and another, and I have a normal ordered operator, okay, where all the A daggers are on the left, all the A's are on the right. What does it give me? Very simple. All the A's act on the right, give you Grassmanns. All the A daggers acting on the left give you other Grassmanns that I denote with a bar. Okay? And that's it. And now, but then what I get, but let me just do it, right? So let's say I have some product of some alpha, A alpha dagger, and product over alpha prime of A alpha, and I want to compute a matrix element between two coherent states. What do I get? So I get the product of, if I keep the order, I don't pick any minus signs. I have a minus pi over alpha A alpha bar, yes, and the product of, okay, but then I'm left with this object. Okay, and as you remember, for the bosons, for the coherent states of bosons, we discovered that it's an overcomplete set, and this overlap didn't give a delta, it gave some exponential, okay? So to be able to compute this, we need to take the complex, the Hermitian conjugate of this, and it is actually, okay, now we have to be also very careful. Yeah, have to be careful about the order, right? Every time, so there's a minus sum over alpha, but now I have, here I will have A alpha and alpha bar, okay? This is what we get. If we do it, is that correct? Yes, that's correct. But now what if I can change the order, if I change the order of A and eta, I pick a minus sign. So this can be expressed as e to the plus sum over alpha eta alpha bar A alpha. Okay? Now, if I take this expression with some eta prime and this expression with eta, and I take and I compute the matrix element or the overlap, so eta prime eta, you can convince yourself that this will give exponential of actually, this is exactly what we got for the bosons. Here we have to be a little careful with this minus sign to get, because the wave, the state, the coherent state has a minus sign, but the overlap is still giving you something that looks like an overcomplete, but not exactly, because remember the etas are Grassmann variables. Okay. But this is already, again, it's a simple Gaussian function, and you can already see that given this expression for the matrix elements, we can play the same game we played for getting the path integral for bosons. What do we do? So let me do it systematically. But we have to be careful about the order. Every time we do a switch, an odd switch, we have to change sign. So a lot of things will be the same, but some things will not be exactly the same. Now, because of this overlap being exactly the same exponential function, if we now want to write a resolution of identity, so from this it follows that resolution of identity for in terms of fermionic coherent states, what we have to do, we have to divide, so we cannot, again, we have to keep in mind that these are not orthonormal, this is not an orthonormal basis, so we have to divide by this factor. And it's exactly the same story, so this will give me eta the differential times 1 over the so this also implies that eta with itself is not 1, but it's sorry, here I made a mistake, I forgot the prime. Okay, so this eta prime, it's a different set of numbers, sorry about that, okay? But if it's the same eta, then we get in the exponent just I denote it as eta alpha bar. Okay. Okay, but now in order to get a resolution of identity, I have to divide by this. So once again, I have e to the minus sum over alpha bar, but we have to remember that these are independent variable, all that story times eta. Okay, this is our new resolution of identity. Red frame. Okay? right, okay. So we're now in business, and let's do the path. Let's derive the path integral representation of a partition function. And I don't need this anymore. And in fact, I'm not going to repeat it because it's just the same trick. Okay, we divide our e to the minus beta h to time slices, and we place a resolution of identity, this one at each step, and all of that is the same as in the bosons, but there is one subtlety. Let me start from the beginning, which is how we define the partition function. It's a trace over e to the minus beta h, okay? One canonical, okay, and I'm not writing the Hamiltonian, but it's again, it can have one body, two body, whatever. What is this? In terms of a complete set of many body states, for example, Fock states for fermions, let me call them lambda. It's a sum over lambda times the diagonal matrix element in state lambda. Okay, so here lambda is a complete set, not of coherent state, and I want to replace it by a path integral. So what do? The first step, the very first step, was to put here a resolution of identity, but it's this one, okay? D eta bar, d to the minus, let me just write because eta bar, eta, okay? I want to put it here inside. Let's see what we get. So it's going to give me a...
Don't you need the sum of alpha?
Sorry?
Don't you need the sum of alpha?
Yeah, so this is an implicit way of writing. Let me just...
Scalar product.
What?
It's a scalar product.
Yeah, it's a scalar product, exactly. So eta, yeah, it's exactly right. It's just a shortcut notation for this.
It can even be an integral, right?
It can be an integral, of course, if alpha is a continuous, like momentum in infinite space. Or, sure, yeah, of course. Okay? Okay, but so let me just write it very carefully, because again, everything is like with the bosons, but every time we have to do a switch, we have to stop and think. That's all it matters. So I'm writing it as, let me, with your permission, I want to change the order of integration and sum over lambda, okay? However, I cannot change this. I have to keep between lambda and okay? So, all right, so I do integral d eta bar, I don't touch it. I can also leave this factor without changing anything, and now I have sum over lambda of lambda and eta, right? And then I have eta e to the minus beta h sandwich with lambda. Okay? Now, remember what we did for the bosons? We took, now these are all numbers. Okay? But in our case, they're not regular numbers anymore because so this thing includes when I act, so the Hamiltonian now contains A's and Heideggers. When I act on the left-hand side, I have some eta bars, okay, and stuff. So now what I want to do is to reshuffle this number here. Why I want to do it? Because then I will have a resolution of identity with the lambdas. But I have to be careful because whatever, this is indeed a number, but it's a number that depends on, this number contains some etas, right? Why does it contain etas? Because what is lambda? Lambda are some Fock states. What is a Fock state? Something with a dagger acting on, right? And because it's the Hermitian conjugate, it has a operator. It has annihilation operators acting on the coherent state, which will give me eta alphas times something. Okay? So altogether, this is a function of eta alphas. This is some function of eta alpha bars. Eta alpha and eta alpha bars are independent Grassmanns, but they're all Grassmann variables. So if I want to switch them, and everything here, any appearance of any eta will be only to linear order because there's nothing else, right? So in other words, if I switch this here, I can do it, but there is a minus sign. Okay? There's always one exchange between some eta L alpha and some eta, and it's eta alpha bar that I have to switch. I have to do an exchange and pick a minus. So, as a result, what I get is let's write it from scratch. I get that Z is this differential with this measure and times. Now I have the sum over lambda of eta e to the minus beta h lambda eta. Okay, that's what I have, and minus sign. Very, very important minus sign. Okay. And now I can do the trick that I did for the bosons, which is to notice that sum over lambda, this thing is just resolution of identity. I can eliminate it. And what I get is, let me write it more transparently. So I'm getting that actually let me write it upstairs because we're already done with this. It's going to be And now what I have here is minus eta, and I have my imaginary time evolution, and it ends with eta. This is eta, this is a coherent state eta, and I moved the minus sign inside, so this is a coherent state minus eta. Okay? And what I do next is repeat the trick of what we did for the bosons. And it's exactly the same. It's exactly the same, because what I do, I take this exponent, I write it as a product of things with d tau, and between each of them I put resolution of identity. And since I'm writing H with normal order, all the A's act on the right. I'm basically using this formula at any order, right? So any function of A and A, dagger and A, that is written in normal order, will give me a function of all the A's replaced by etas, all the A daggers replaced by eta bars, and and when I take this number out, I get this overlap. But this I also know.
It will be minus eta bar, right?
What is the only difference? The only difference is, and I now do, so between the initial and final, now, just like in the bosons, I want to think of this as eventually I'll take the continuum limit that the number of stages is going to infinity, and the tau goes to 0, namely the index goes to a continuous variable which I call imaginary time tau, and the initial state is eta of 0, the final state is eta of beta. Okay, so eta, so I'm going to get eventually a continuous variable, eta tau. Okay, and eta tau is of course an array of eta alphas, and I have boundary conditions, but the boundary condition, the only difference, everything will, all the mathematics will be exactly the same as the bosons. I don't even repeat. Actually, the fact that I have here, I will also have the overlap between eta of tau and eta of tau plus d tau. And then with the opposite sign to this, it will give me a time derivative. Everything will be the same. What is the only difference? The boundary conditions in the time direction, right? Because it is not periodic, it is anti-periodic. So the path integral at the end, I'm going to get this purple one is there. So Z is, we write the final result. It's going to be, so there will be some differential capital D, which I define in exactly the same way as before. It's a product, the limit, n goes to infinity, blah, blah, blah. Don't even write it. The only difference is there's no factor of pi. Okay? That's all. And that it's not, these are not complex numbers and all that. But it has the same form as in the bosons. And now I have here an action which I will write in a minute. the action is some functional of these etas and eta bars, written of course in the correct order, but what is the difference is that the boundary conditions are, and you know what, at this stage, let us not even call them eta, let's call them psi, okay? Let's call them the same name that we have for the bosons. Not that it's important, but I want to eventually have a uniform thing, right? Sorry, I erased it, and I do want to keep this. This is just something I want to keep. Okay, so this is S. Okay, I write it in the middle, but here psi of 0 is equal to minus psi of beta.
You mean zeta?
Hmm?
You mean zeta
Well,
instead of the minus? Don't you want to put zeta?
no, so here I'm doing it for, you're right, I want to write, this actually is zeta, but let's do it for fermions, okay? You're right, I mean,
This notation is for both.
this is for fermions, okay? Let me write it, use the red color for fermions, okay? But you're right, if I want to write a general expression, I need to put here a zeta, but I'm going in a minute to show you what is actually the difference. Why does it matter? What are the boundary conditions? Because just let me first write the action, okay? What is the action explicitly? So it is an integral from 0 to beta of, first of all, you have a one-body term that is, and let us write it in a diagonal basis already, okay, not to worry about it. So the first term is psi bar, so there's a sum over alpha, psi bar d tau plus psi of alpha, and this is psi and psi bar at tau. Psi, just like before, is epsilon minus mu. This is the one body term, and plus some, actually let me write it like this, plus S interaction that I don't even write, okay? But it has the same form as in the bosons, with its one integral over time and all that. And we just have to remember that the psi and psi bars are Grassmann variables, but it's the same expression. Okay? Now, just the last step that wants to bring it to a form, this is the first term. The first term is what we want to call S0, the non-interacting part. And if we didn't have interactions, we can exactly solve for the partition function, for the free energy, for everything, right? Because they are Gaussian integral. But we're missing one step, which is to go to the Matsubara frequency. But this is exactly where the boundary conditions are different. Okay. they're going to give something different because let me write down, so just like what I did for the bosons, I want to express the psi alpha of tau as a Fourier series, right? So I have a factor of normalization factor of 1 over square root beta, sum over n, psi n alpha e to the minus I omega n tau. Okay. And before, for the bosons, we had periodic boundary conditions. So just like any periodic function, we knew that these omega n's should be integer multiples of the basic period 2 pi over beta. But here we have anti-periodic boundary conditions. So suppose I'm just writing this and I'm not telling you what are the omegas. This function of tau has to satisfy that psi of 0 equals minus psi of beta. Okay? So, I'm going to write it over here. Okay, so let's do it. So, psi of 0 has to satisfy. Let's write it explicitly. What is psi of 0? It's 1 over square root beta, sum over n psi n alpha, and this factor will give you 1, right? But it has to be equal to 1 over square root beta, sum over n, psi n alpha e to the minus I, sorry, it has to be equal to minus the same thing, but with e to the minus I omega n beta. Now, in order for these two sides to be equal, I must require that e to the minus I omega n beta equals minus 1, right?
Mm-hmm.
But what is minus 1? If I can always write it as an exponential of e to the I pi. Okay? So the exponent here has to equal pi up to integer multiple of 2 pi. As a result, what is the formula for omega n? It's going to be 2n plus 1 times pi t. Okay? An odd multiple of pi times t. Okay, and this is yeah. So that's it, and then we can, if we just have a non-interacting problem, we can switch to Fourier space using these Matsubaras, and everything will follow the same. You'll have a sum over n, it's diagonal in n, and everything is great, except that the values of the Matsubara frequencies are shifted by half period, okay? Oh, sorry, by half frequency, to account for this factor pi, for this minus 1. And the consequence of that, so if I now repeat let me now write down general formulas for bosons or fermions using this factor zeta. Okay? Okay, so I'm erasing this. And this is just for non-interacting problems. So this is for v equals 0. Okay, so z naught is, it can be written as and let me even use the same notation. So remember, for the bosons, we showed that we can replace the action by the non-interacting Green's function. And the Green's function has exactly the same form. It's 1 over minus I omega. Okay, so all of that is exactly the same. But the result of this is the determinant of G naught to the power minus zeta. Okay? Okay, so this is the sort of its zeta and psi look too similar. Okay, it's minus zeta. So in the case of fermions, we get the determinant of the Green's function. Is that right? No, sorry, it's the, so, yeah, sorry. In terms of the Green's function, it's just the zeta. Okay, so for bosons, I get the determinant. Hold on, now I'm confused again. Just a minute. Fermions, it's, yeah, that's fine. For fermions, I get the determinant is the same, is of the same matrix. Okay. Okay. For bosons, it's going to be determinant of G naught, which is the inverse of A, or of the action. Okay. And then let us write it explicitly. What is this? So this is the product over n's and alphas of I have to be a little careful. So it's beta minus I over n plus psi of alpha to the power minus zeta. Okay? Okay, this is an explicit expression. And therefore, if I take the free energy, which is minus 1 over beta times log z. I'll write it explicitly. Is going to be minus zeta times t times sum over n log of the stuff beta minus n plus psi. Okay, that's a free energy. So the zeta comes in as a 3 factor, it's either minus or plus. And most importantly, this is something familiar. If we repeat the calculation of the occupation of N alpha,
Looks like,
sorry,
isn't there like an extra minus sign?
sorry, I forgot here, there's also a summation of it. What?
The minus sign before the zeta.
Let me see, so it's,
Because you have the minus sign of the zeta in the power.
no, it's fine, because, so it has minus zeta here,
Right.
right? So when I take the log of this, it gives me minus zeta
Right,
times
but
the
you
log.
also have a minus before the t.
That's right. That's right. Yes, you're right. Yes, yeah, right. Right. Thank you. Yes, good. Okay. Right. Okay. So now the N alpha, which is just repeating the same calculation, it's going to be the sum over the Matsubara sum over the G naught, right? Which is, if I write it explicitly, it's N. Wait. So let me just check something. Where does the so right, so where does the zeta come in? Yeah, so the zeta comes in. If I plug in the expression for G naught, there's a minus zeta times t times the sum over n 1 over I omega n minus psi alpha. Okay? So for bosons, I get back the same thing I had before, which is this minus, so zeta is 1, and then the minus will turn it into minus I omega plus xi. For fermions, I have an opposite sign. And when I do the Matsubara sum, and now there is another difference, because in this sum, the Matsubaras, okay, let's write them explicitly. The Matsubara omega n is 2n, sorry, it's 2n plus 1 minus zeta over 2 times pi times t. Okay? This is what they are in general. So with zeta equal 1, this vanishes and I get an even integer times pi t, and for fermions I get plus 1. Okay? Okay, so in all these expressions, I have to remember that there is a different formula for the Matsubaras, and that's what's important for the result. Because then if I do this calculation for the fermions, what will I get? After the Fermi-Dirac. So in general, what I'm getting is that n alpha is 1 over e to the beta psi alpha minus zeta. Okay? Either Fermi-Dirac or Bose-Einstein. Okay, so I guess that's exactly it for today. And next week, which is the last lecture, I'm going to show you a trick how to deal with the interaction. We don't have a lot of time, but I'll just sketch one of the things that you can do to make progress. Okay? Okay.
תודה רבה.
תודה רבה.
Thank you for the attention.